Good morning, all. And today we are going to talk or introduce a little bit about instrument transformers. Having said that, let's ask our straight with start with the first question. Why do we need instrument transformers? If I have a 400 kV system and the continuous current is say 1600 amps or 2000 amps, I do not have any measuring device directly which is capable of measuring 400 kV and 2000 amps. It's a challenge in manufacturing a measuring device to handle higher voltage and higher current. Then I need some equipments which scale down the value to be measured at a well-known predefined ratio, either voltage or a current, and that ideal device is our instrument transformers. If you want to measure 400 kV, you need to insulate that metering equipment or measuring equipment to 400 kV, even if that may be technically possible, but commercially definitely it's not viable. So we need a device which converts this 400 kV to a small value so that a measuring device can measure this value. And if the predefined scale down ratio is known, then by means of measuring the small value, by means of multiplying this ratio, you will be able to know what's the value, what's the real value, right? But of course, though we call this like a predefined ratio, like maybe 2000/1 as a CT ratio, or 400/√3/110/√3 as a VT ratio, it's not really ideal. Seems like ideal, but like in reality there will be some errors. We will be talking a little more on that also. And in order to eliminate that, like what are the new trends, technologies which is available, and how it eliminates or minimizes that error, that also we will see. Instrument transformers are not measuring devices. Instrument transformers convert or changes either voltage or a current from the highest value to the quantity which it could be measured easily by measuring device with a well predefined ratio. Current transformers, why, what? Like I have given an example with respect to 400 kV system with respect to the voltage. I mean, what's if you want to measure 400 kV, you need to insulate the measuring device with the 400 kV insulation. If you have even a low voltage, say example 415 volt, and that insulation is not really a difficult call. But if you want to measure a current of 2000 amps, 4000 amps, 5000 amps, or 6300 amps, it's difficult, if not impossible. It's not commercially viable, if not technically viable, to measure such a higher currents directly. Measuring 2000 amps, measuring 3200 amps, measuring 4000 amps, or measuring 5000, 6300 amps is not directly possible. At least commercially it is not attractive by a measuring device, because if it has to measure 4000 amps, this has to carry 4000 amps, and that's not practically possible. And of course the current has to be scaled down to a predefined ratio. How the voltage transformer changes the voltage of higher voltage to the lower voltage in a predefined scale, the same way current transformer scale downs the current from the higher current value to the lower value. And of course there are two different type of instrument transformers. One is a current transformer, other one is voltage transformer, right? Voltage transformer also can be called as potential transformer. But in both the devices we have two different combinations. Whether this instrument transformer you are going to use it for protection or measurement, whether you are going to use this device CT or VT, is it for metering or is it for a protection? How does it has an impact on selection of the CT or VT? Anyway, I need to step down 4000 amps to a well-defined ratio so that it can be measured, and I have to identify that as a 4000. But like, how does this measurement, if the instrument transformer to be used for a measurement, why that has to be different from the instrument transformer which has to be used for a protection? Why we need to have a different property or different behavior of measurement device? That means if the instrument transformer gives an input to the measurement device, that has to behave differently, whereas if it is given an input to the protection doesn't really mean without measuring it is protecting. Of course it's also measuring, but like the ultimate goal of the measurement is to measure that value in terms of measuring current, in terms of measuring energy, in terms of measuring power, in terms of measuring power factor, etc., etc. If in terms of protection, that's pretty much protection, which means that function is to decide whether it is a fault or not and gives a trip command to the circuit breaker in case it's a fault. And why it has to be different? Because the expectation of measurement is different, expectation of protection is different. Let's come to this point maybe a bit more closer. Measurement. I need to be accurate. I need to be accurate as much as possible from 0% to 100% of the rated current. Let me repeat my statement. It looks very basics, but what is basics is also easy to miss. The device, objective of a measurement device is to measure either current, voltage, power, whatever it is, accurately from 0% of a value to 100% of a value. What I mean, say example, if I have a 2.5 MVA transformer, 11 bar 0.433 kV, LV side, the rated current will be like 3333 amps. And probably I may be placing 4000 amps CT there. And if the CT, if I am giving to the meter, a meter, multifunction meter, or energy meter, whatever may be the meter, the objective of the meter has to be accurate as possible when the current is from 0 amps up to its rated current. When I say rated current is 1 per unit, from 0 per unit to 1 per unit, it has to be accurate. And the current will never ever go beyond the rated current because that's the maximum capability of the device itself. And the only probability when this current can go higher than the rated current is a fault, or maybe some momentary events like motor starting or a transformer energization, etc. But that's very rare probability. Even if that happens, that's very short time. And accuracy above the rated current is not really mandatory for a measurement devices. Accuracy from 0 amps to 3300 amps or 0 amps to 4000 amps important for a measuring device. But like means or say, you don't really care when the current is 8000 amps or 16,000 amps or 25,000 amps, which I guess like 16 kiloamps or 25 kiloamps or 40 kiloamps, which is the current not because of the load, but because of the fault. So the expectation from the measurement device on that instrument transformer, which we call measurement CT, is accuracy has to be maintained from 0 to 100%, and above 100% I don't really care about the accuracy. And means what say, above certain value, like you should not reproduce the current in the same ratio to the secondary. If it does, then probably there is a probability that this measuring device itself will fail. That's because the measurement device do not have the capability to withstand infinite current. Say example, if I have a 400 bar 1 CT and fault current is 40 kiloamps, the reflected fault current will be well known, right? 40,000 divided by 400, so it's 100. Whether this measurement device which you have installed, whether it's capable of withstanding 100 amps is a question mark. So the ideal expectation on the measurement device is this has to faithfully reproduce what is available in the quantity to be measured, which is on the primary, in the ratio, well-known defined ratio, accurately up to the rated current. And after the rated current, it need not really worry about anything. And after certain value, it has to stop reproducing it. But protection, it's the other way around. It need not really worry about from 0 per unit to 1 per unit, which I mean up to the rated current, accuracy is not important at all if that CT input is given to the relay, because anything less than the rated current, I'm not going to trip the circuit breaker. So when my rated current is 3300 amps, actual current flowing is 2000 amps. Even if my protection CT measures it's 1000 amps, I don't have any problem. But on the other side, the important or like the essential factor which has been looked out from the protection instrument transformer is it should be faithfully reproduce what's available in the primary for the higher currents. So from measurement device, the expectation is you have to be accurate from 0 to 100%. Whereas protection device, you need not be accurate. I'm not saying you should not be accurate. You need not be accurate, but the device should be accurate, or it has to, even if not accurate, it has to faithfully reproduce what is available. Like the terminologies are different. It's not really accurate. Like I never care about whether it is 20 kiloamps or 20.13 kiloamps, but it's important, like it has to differentiate whether it is a fault or not. So it has to faithfully reproduce the waveform. That means it should not saturate. It should not change or alter the shape of the waveform. And that's the expectation of protection CT. And obviously then like the same device which cannot really do both together. That means an instrument transformer which is designed, the core material which is designed to reproduce with a higher accuracy from 0 to rated current may not be able to retain the same accuracy, or I mean it's a capability at like 10 times the current or 20 times the current. So the property of measurement device and protection devices are different, and hence like you needed two different CTs. And nowadays the trend probably, I mean, to say we have some instrument transformers which can club both the functions. In fact, CT and VT also can be clubbed into a single device. If you have any idea like what is the device, can you just tell me? With the recent trends, we don't really need two different devices, current transformer and voltage transformer, measurement CT and protection CT. There are simple devices which are available, which takes care of measurement of, not measurement of, scale down of voltage or current, scale down of voltage and current, and it's accurate from 0 to like maximum fault current. There are devices nowadays which are available. Fiber optic current sensors, also called as FOCS, FOCS, right? They have the capability to measure voltage current, in the sense like step down the voltage and current to give probably as accurate as possible from 0 value to whatever may be the maximum possible value. No saturation, accuracy is amazing, right? And single device is probably enough. What is harmonics? The waveform is not sinusoidal, and it's a non-sinusoidal waveform, but it's a periodic waveform. Then probably through Fourier transformer, we are converting that non-sinusoidal but periodic waveform into sum of sinusoidals and cosinusoidals, which means second order, third order, fourth order, fifth order harmonics, etc. comes in. And we are measuring the harmonics directly at 11 kV or directly measuring the rated current of like 2000 amps, 1600 amps. No, we are using voltage transformers and current transformers. And this voltage transformer and current transformers are basically inductive in nature. And reactance of this inductance is proportional to the frequency, which means, like say example, there is a 23rd order harmonic. My CT offers 23 times higher reactance than what it offers to the fundamental frequency. And that's the input which has been probably passed to the meter, and we are measuring the harmonics on the secondary, and we are claiming that that will be the same as what's going to reflected by the same ratio in the primary. Like that's not really logical, right? If you got like what I'm trying to say, just got it in chat. Like, of course, I'm talking a little bit on slightly on the technical. Means once you understand what is harmonics, once you have understood what is the equivalent circuit of the instrument transformers and what's the application, like this could be like better understood, right? And of course equivalent circuit of instrument transformer is also the same thing. Like this like I mean, so see here you will be connecting like meters or relays for instrument transformers. That's pretty much it. So you will be having x1 and x2, right? Like of course this is wrong, in fact this is r and this is x, Let's try to pick up maybe the right one, right? R1, X1, R2, X2, right? So means was this X value itself depends upon the frequency, right? XL is 2 pi FL, L remains constant, but F 2 pi F is not constant for fundamental and 23rd order. Like I'm just saying random number 23rd, you can take 5, 7, 11, 13, any numbers, which means the reactance value will be 5 times higher for a 5th harmonics and 7 times higher for a 7th harmonics, 10 times higher for a 10th harmonic. And what is the voltage or a current to be measured when that is reflected on the secondary of the instrument transformer, CT or what, VT, whatever it is? Means what say the behavior of this device is not same for 50 hertz and it is not same for 250 hertz, it's not same for 350 hertz, it's not same for 500 hertz. And we are measuring here, this probably offers like a different effect to what is originally which is available on the real voltage, like high voltage, high current system. And we are measuring in low voltage, low current systems. But like this behavior itself different, and we are like by just a multiplying ratio, like we are assuming the same harmonics there in the HV side, which is not practically right. So what I mean, you may need to have a device here which should not be function of frequency. If you want to measure the actual harmonics, what's available in the line to be measured, your equipment which you're using and trying to convert one voltage to another voltage or one current to another current should not be frequency dependent. But unfortunately, like instrument transformer is electromagnetic device and it has predominantly inductance. It has impact because of the change in frequency. So when you are measuring fundamentals, your error will be some percentage. When you are measuring third order harmonic, when you are measuring fifth order harmonic, seventh order harmonics, like this will be like means what say much more, like the error will be much more. So that's precisely what I'm trying to stress. If you got it now, just got it in chat. And of course, that's not a complete picture, but at least like overview of what it is. If you take maybe fiber optic current sensors, that's probably purely based on optical functions, that doesn't really have any such issues with respect to the I mean what's a change in frequency. And in fact, like you cannot use instrument transformers in DC system, right? Why you cannot use instrument transformers in DC systems? No change in flux. Thank you, Sanjay. Yeah. So if you could have used instrument transformers in DC system, then probably means or say Thomas Alva Edison's DC system would won the war, not AC system of Tesla, right? Like one and only advantage of AC system over a DC system is we have a good option to change the voltage by a transformer principle, which is available in AC, which is not practically possible in DC. So I mean, you need maybe some other mechanism to measure the voltage in DC and current in DC, right? HVDC, if you talk about, like it carries like 6000 megawatt plus or minus 800 kV. But when it comes to the protection, do we have a sophisticated protection like AC system? Answer is no. That's because of how we are able to measure that voltage and current. But like if you take this fiber optic current sensors, it's either AC or a DC, 0 hertz or 2000 hertz, 2 kilohertz, 10 kilohertz, it's immaterial. It measures as accurate as possible, right? And that's also what we have covered in detail of like what is fiber optic current sensors, right? And I guess like that is, at least you might have understood now the difference between like measurement and protection CT. Measurement, it has to be accurate from 0 per unit to 1 per unit or 0 to rated current. Protection, I don't care about the accuracy from 0 to 1, but above 1, like up to the maximum fault current, I expect that has to faithfully reproduce the waveforms. Now let's come to another interesting question as well, that is whether to choose 1 amps or a 5 amps. Whether to choose 1 amp CT or a 5 amp CT. Of course, both has advantages and disadvantages. If you are choosing 1 amp CT, it has higher size. If you're choosing 5 amp CT, the size will be less. But if you're choosing 5 amp CT, the burden connected on the secondary side will be increased by 25 times, I square, right? 5 square. 1 square is 1, whereas 5 square is 25. So the connected burden will increase by 25 times. So you have to be a bit careful when you're choosing 1 amps or 5 amps, right? Like I have given like 2 simple facts to compare. One, what's the impact of connected burden? Second one, what's the size of the CT? But there could be multiple more other things with respect to selecting 1 amps and 5 amps, 1 amps and 5 amps. But like this is means what say much important. One for less cost, Nimesh, that's not really true. As I told, like means what say, if you have 100 bar 1 amp CT and 100 bar 5 amp CT, size of 100 bar 5 amp CT is smaller than 100 bar 1 amps. If everything else remains the same, definitely 1 amp CT will not be cheaper, Nimesh. Yeah, 1 amps has advantage of low VA requirement. Sanjay, that's right. Like that I have probably explained from the opposite direction. The connected burden will be equal to the resistance which is connected on the secondary side for 1 amps. That is, assuming 1 amps current is flowing, I square R is equal to R if I is 1. But I square R equal to 25 R when 5 amps CT, right? When the rated current is flowing, right? After that, let's come back to ask one interesting question. Metering CT has to be connected, or measurement CT has to be connected to the meter, and protection CT has to be connected to the protection, that's the relays. What's the one protection which specifically needs metering CT has to be connected as an input? What's the one and only protection which needs input from metering CT, not the protection CT? Nimesh, burden will decrease, which will need less winding. Burden will decrease, which will need less winding. Not really true. So means what to say? If you're selecting 1 amps, the required burden will come down. But if you're comparing 100 bar 1 10 VA CT versus 100 bar 1, means same 10 VA, like 100 bar 1, 100 bar 5, same VA rating. So obviously, like your 1 amps will be bulkier, right? Fine. Fine. Let me repeat my question to get good answers or better answers. What's the one and only protection which needs input not from the protection CT but from the metering CT? I'm not really moving the slides, Amos. Like I was probably, asking the questions from what's the syllabus which I had. Yep. Like let me give the answer also. It's a low forward power relay or a reverse power relay. Low forward power or a reverse power is the protection function which needs differential protection, definitely needs some special class of a protection setting. The one and only protection in the world which needs the input from the metering CT is low forward power or a reverse power, because that's kind of detecting undercurrent, right? So you have to be accurate enough from 0 to 100%, not the other places, right? Like, and of course you have like multiple types of CTs, metering protection, and metering itself, like you have different classes like 0.1, 0.2, 0.2s and so forth. Yep. So 0.1, 0.2, 0.5 and 1. And in addition to that, like you might be having 0.2 yes, 0.5 yes, right? Like 1 up to 1 is quite common, 3 and 5 is kind of like very rare. So you can just look at this 0.2s and 0.5s, like these two images, I guess, like good images. So 0.1, 0.2, 0.5, 1, and 0.2 and 0.5, you have a special class, this one, which has an extended accuracy. And like here, like you have at how much percentage of the current, how much percentage is the error. When you say 0.1 is accuracy class, the ratio error is 0.1 at 100% of the current. But when the current comes down to 20%, the error is 0.2%. When the current is 5%, the error is 0.4%. And less than 5% of the current, there is no accuracy guaranteed. Which means if you have 100 amps, 100/1 CT, if the current flowing on the primary side is say 4 amps, there is no accuracy guaranteed from the current transformer perspective, even if you are using 0.1 kiloamps, sorry, 0.1 class CT, that may be reflected as a 0 amps in your meter. Most of the time we blame the metering manufacturers for that, but that's the incapability of the CT, not really the meter. If you got what I have told, just got it in chat. It's another important information. The CTs, electromagnetic all instrument transformers, have the capability to measure the current only from 5% to 120% if it's a normal class CT, and if it is probably special class CT, still it has capability only to measure from 1% to 120%, which means less than 1% of the current in special class CTs and less than 5% in normal class CTs. There is no accuracy guaranteed below this value. If you are using any of the CTs, if you are using 100/1 CT or 100/5 CT, if the current is less than 5%, 5 amps, there is no accuracy guaranteed in the output. Output can be 0 also. And you will be specifically facing this problem in most of the places. Multiple examples: solar plants during night. CT ratio should be selected in such a way that like it's higher than the rated current. But during night time, the auxiliary power of the solar plant could be like 0.1%, which means definitely less than 5%, right? So obviously there is no accuracy guaranteed. So it's one really tough challenge. And similarly, like when you have like some power plants which you are using in starting stages, or like the plant is off, you are consuming only the auxiliary power from the grid, etc. Wherever you have a power plant and you are consuming only for the auxiliary, this scenario can occur, where you will face a challenge that CTs are not accurate enough and they are not driving the values. And like you will be having very higher ratio CTs, that's to cater the full load, but by such durations you will draw very small quantum of power and you will not have accuracy from CTs, and sometimes the CTs may not even drive the meters. So it's just not that, like, means what say, when it comes to like what we have seen here is the metering CT, like you have probably a protection CT in multiple access, like protection CT, you have normal class, that is 5P class or P class. Then like with respect to IEC, you have like PX, PY, PZ, TPX, TPY, TPZ, right? So I'm not really sure whether you are aware of all these things: TPX, TPY, TPZ class CTs. So they are like a special class protection CTs. They are special class protection CTs. TPZ is needed for high capacity generator differential protections. TPZ, let me check whether we have, yeah, TPZ, like wide transient performance. Like when you have distance protection with auto recloser, you may need to think of TPY CTs. If you have large capacity generators with the extremely high X/R ratios, for their differential protection, you need TPZ CTs, which means what say, the DC component plays a crucial role with respect to CT saturation. and transient performance is extremely important. It's just not measuring the RMS current, it's measuring the actual current is also important, because faults are determined or identified using fast Fourier transform algorithms in the sophisticated relays even less than 3 or 5 milliseconds nowadays. Your overcurrent relays or earth fault relays may take 1 cycle or 2 cycle, 20 milliseconds or 40 milliseconds to detect whether it is a fault or not. But like the algorithms available in the relays, distance relay or a differential relay, now capable enough to identify whether that's a fault or not in 3 milliseconds. In 3 milliseconds, you may not have finished 1 cycle in the fault current. And in the first 3 milliseconds, you will be having a predominant DC component. And if your X by R ratio is high, the DC component is extremely high. And you need more accuracy CTs for such scenarios. And you may need TPY CTs for distance protection with auto recloser facilities, and TPZ CTs for large capacity generators differential protection. So one is a magnitude, other one is an angle, right? So a sinusoidal wave is probably reflected as the same sinusoidal is one aspect, and the second aspect is it giving with the same angle? That's pretty much the second aspect of it. So whenever you are measuring, you have two errors. One is of course a magnitude error, other one is phase angle error. This phase angle error is not really going to cost you much when it is non-directional overcurrent and earth fault, but this phase angle error is going to be a biggest challenge in differential protection. Why? You have one CT at one side and other CT at another side. If they have a phase angle, even though if the magnitude of the current remains the same, because of the error in the CTs, that it is reflected as probably two different currents on the LV systems, and that may give a mal operation to the relays. So your normal overcurrent and earth fault relays just need accuracy with respect to magnitude, but other special protection needs not only the magnitude but also the angle. And what's the error in the phase angle is the phase angle error. So we have covered introduction to instrument transformers, like why current transformers, what it is, what are the types, what's measurement versus protection, like when to choose 1 amps, when to choose 5 amps, why to choose 5 amps, especially for high capacity generator applications, how to select ratio, burden, instrument safety factor or security factor, ISF for metering CT, what is PX class CT, what's the knee point voltage, what are the standards, what are the type test and routine test, protection CT sizing and metering CT sizing, including CPCT selections, protection CT sizing for unit protections, that is like PS class with Indian standard old one, now it has been again replaced by PX class, PX, TPX, TPY, TPZ, where it is important with respect to its behavior during the short circuit and whether it saturated or not. So you have to be, carefully select the CT based on its like saturation. So if the fault current is more than 31.5 kiloamps, you cannot choose 31.5 kiloamps CT. You have to go with the 40 kiloamps CT only. What happens to secondary when CT gets saturated? That's means whether the CT has driven into partial saturation or a full saturation. In fact, like that Excel what has been there here, I guess CT saturation calculator Excel, right? Like it's a downloadable resource which you will be able to download. That will show you the graph of what's the output CT current, depends upon the like fault current and CT selected, and of course CT ratio. So CT output will not be zero like we think. There is no digital point where this one will become zero. Answer is no. CT will not saturate 100%. Is it a partial saturation? Like output will be a distorted waveform. Distorted waveform depends upon how depth the CT is saturated. It will not faithfully reproduce the waveform. That's the only thing which you can probably say. But like more, you will be getting this. I mean, for say in CT saturation calculator Excel, like that will give you the output waveform of the CT when like CT is driven into partial, and like output becomes 0 is like extremely worst case, that nowhere in fact practical. Again, directional overcurrent also, I have not really worried much about it, because in general, like the systems are inductive in nature. So with respect to the voltage, current lags almost close to 90°, right? Assuming R is 0, but like R has some value. So this angle will be like in the range of about -80 to 90. So fault is in the forward or a reverse could be easily identified, and that errors may not have that much significant impact. So directional overcurrent also, like here, like direction, like differential relay, if there is a phase error, it's reflected as a big mistake, right? So if I am missing, say example 30° error, then sine 30 is 1/2. Like I'm comparing a magnitude of 0 with 0.5, even during normal, like that will detect that as a fault and it will trip. So that's the reason why it is important. Directional overcurrent also, it is not that significantly important. Thank you all. Thank you so much. Have a great day.